Swayam Prabha. Digital India. Educated India.
Welcome. In this series of lectures, we are going to study about Organic Chemistry 3 paper. In the Unit 1, we will be studying about nitrogen containing functional groups. The first lecture we will be focusing on nitro compounds. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha,
MHRD, New Delhi.
So let us look at the various topics that we will be studying in this particular session. We will first start our study with the structure of nitro compounds. What are the various resonance structures and how they are related to each other, we will be looking at. Then afterwards we will be studying about the preparation of nitro compounds, basically from alkyl, halides and amine, how we can prepare nitro compounds we will study. After that we will be studying about a few industrial process, mainly the liquid phase and the vapor phase methods. We will also do a comparison between these two methods. Then we will study about reactions of nitro compounds like reduction, hydrolysis, halogenation, etc. we will study, and we will study few name reactions like Henry reaction or the nitroaldol reaction, Mannich reaction and Neff reaction, which produces ketones from nitro compounds we will be studying. In this session, we are going to study about nitro derivative. So in the beginning, we will just have a brief overview of what are nitroalkanes. So the nitroalkanes have a general formula RNO₂, and if we are going to do a nitration reaction, we have various reagents which are used for the nitration, which include dilute, concentrated or fuming nitric acid, or metal nitrates like sodium, mercury or silver nitrates. We can also use a combination of nitric acid with other acids like acetic acid, sulfuric acid, acetic anhydride, or in solvents like chloroform, etc. we can use for nitration. And we also have mixed acids where the mixture is basically nitric acid and sulfuric acid. The nitric acid what we may be using may be concentrated nitric acid or fuming N2O5 or even N2O. So these are all the various nitrating agents, and when we are going through many of the synthesis for nitro compounds, we will be looking at each reagent separately. And if we look at the reaction mechanism, what we are going to see is there are two major type of reaction mechanisms available. One is in the aromatic system, it is a electrophilic substitution reaction. That means NO2 plus ion is involved as the intermediate in these kind of nitration reactions. When we go to the aliphatic system, many of the reactions are basically radical addition reactions. So the major difference between aromatic and aliphatic nitration is, in aromatic system, it is a substitution reaction and it is a electrophilic substitution reaction. And in the case of aliphatic systems, it is a radical reaction and it is a addition reaction. So these are all the major reaction mechanism for nitrations of both aryl and aliphatic systems. And of course, we will also look at what are the important uses of various nitro compounds. Nitro compounds are generally used as solvents, dyestuffs, pharmaceuticals, explosives, and as intermediates for the preparation of amines. So these are all the various applications. So this is a brief overview about nitroalkanes. Let us look at the molecular formula of nitroalkanes. So we have a general formula like RNO₂. So this RNO₂ can be written in two different forms. That means they can be represented as RONO or they can also be represented as RNO₂. These two representations are isomeric representations for nitroalkanes. We are going to see which is the correct one for the nitro compounds. So when we look at the reaction of RONO, this RONO on reduction gives alcohols and ammonia or hydroxylamine as the product. So this is one type of reaction. So in the presence of 3 hydrogen molecule, the RONO can be converted into alcohols. So this compound is basically, that RONO compound is called as alkyl nitrite. As you have seen, these are basically esters. So when we hydrolyze, so the alkyl nitrates are considered as esters of nitroesters of alcohol. when we look at the normal RNO₂ type compounds, the RNO₂ type compounds undergo reduction to give primary amines. So basically what we can say is we know nitro compounds can be reduced to amines. So in other words, the general formula for RNO₂, that means nitroalkane, is RNO₂. And RNO₂ plus 3 hydrogen gives amine and 2 water molecules. So we can confirm that the molecular formula for nitroalkane is RNO₂ and not RONO. So if you are going to write general structures for the nitro compounds, we can write inductive effect. This structure actually shows like an inductive effect. So these are all the two resonance structures. Here we have no charge on either nitrogen or oxygen. So this is one way of representing nitro compounds. This is in old textbooks and other things, you will be looking at these kind of bonds where nitrogen to oxygen is written like a coordinate bond. In recent general books, you will be looking at the plus and minus charge in nitro compounds. This is how people represent. So one of the oxygen may be having a negative charge. In the resonance structures, the other oxygen is having the negative charge. So when we have these kind of two resonance structures, we can actually write the overall structure as shown here, having oxygen having half the negative charge in one of the oxygen, and the other one also is having half the negative charge, and nitrogen is having plus here. So this is minus half and this is minus half. So that is how the total charge -1 is distributed between two oxygens. How do we know these resonance structures actually exist? So there are various evidences which are available which confirms that we have a resonance structure. The first one is the NO bond length. What we are going to look at is actually 1.21 angstrom, and which is actually less than the NO single bond. Generally the NO single bond length is 1.36 angstrom, and the NO double bond is having 1.15 angstrom. So the NO bond length is 1.21, is in between 1.36 and 1.15 angstrom. And we have also seen the nitro compounds have a very high dipole moment, that is 3.5 d/2 4.0 d/. This indicates that there is a full positive charge on nitrogen and half negative charge on each oxygen atom. So this is the next evidence to show that there is a resonance structure for nitro compounds. And also we have seen that the nitro compound is actually isoelectronic with RCO2-, that is carboxylate anion. So when these are isoelectronic, we can actually say that they will have more or less similar structures. In other words, what is the structure of carboxylate anion, which is very similar to be nitrate ion also. So we can draw the resonance structures, and we have the evidences to prove that the resonance does exist. So here, as we have mentioned, one of the oxygen is having a partial negative charge and another one is also having a partial negative charge. So when you have two partial negative charge and the nitrogen is having a full plus charge, so there is a charge separation in this molecule, due to which we have a high dipole moment. And we can also write all this, the bond. Partially this bond is a double bond and this is a single bond. And in the other resonance structure, the top bond becomes a double bond and the bottom one becomes a single bond. So in other words, we have a partial double bond character and a partial double bond character in the top also. So in other words, the actual bond length is lesser than the either the single bond or the double bond, which clearly tells that a resonance exists. And as we have also seen here, the carboxylate anion and the nitrate groups are having very similar or isoelectronic structures. So these are all the evidences which tells that there is a resonance exists for the nitro compound structure. And if you look at the hybridization, there is the nitrogen is basically sp2 hybridized in this particular compound, and it actually forms 3 sigma bonds. So what are the 3 sigma bonds? There is 2 oxygen atom and there is an alkyl group. So all the 3 will form first sigma bond, and then there is a pi bond also which is present between nitrogen and oxygen. So these are all the resonance structures and the bonding in nitro compounds. Let us start with the various preparations of aliphatic nitro compounds. We will first start with the nucleophilic substitution reaction. Here alkyl halides or organols sulfates with the metal nitrate salts reacts to give the final nitro compounds. There is also free radical nitro addition. As we have mentioned, alkyl substituents undergo radical addition reaction. So we have a free radical nitration alkanes. This actually happens at the gas phase at 350 to 450 degrees centigrade under pressure. This reaction actually occurs. This is an important industrial process. And we also have oxidation of oximes or primary amines, which leads to nitro compounds. We also have reduction of beta nitro alcohols or nitroalkanes, which give nitro compounds. We can also prepare aliphatic nitro compounds by decarboxylation reactions. Alpha nitrocarboxylic acids undergo decarboxylation to give nitro compounds. Let us look at the first one. This is a nucleophilic substitution reaction. So here we are looking at the preparation of nitro compounds from alkyl halide. So there are various reactions we had given here. First one is the Victor-Meyer reaction. So heating an alkyl halide with silver nitrate, that is in the presence of aqueous ethanol, gives this product. So here is a reaction given here. The alkyl halide reacts with the silver nitrate in the presence of the solvent. Basically, an aqueous ethanol is used as a solvent, gives nitro compound as the major product. As we have seen, the nitrate ester is also, alkyl nitrate is also formed as a minor product in this particular reaction. And in this particular case, the primary alkyl halide gives very good yield, whereas the secondary or the tertiary alkyl halides give very poor yield. And there is also another reaction called Kornblum reaction. So here, instead of silver nitrate, we are actually using sodium nitrate. And when we use sodium nitrate, this actually gives a better yield for the secondary alkyl halides. And when we look at the reactivity of halides, iodide is highly reactive compared to bromide, followed by chloride. So this is how the general reactivity of alkyl halides. And when we use dimethyl formamide as a solvent and urea as the additive, this actually increases our nitro product formation. That means the minor product, that is the alkyl nitrate formation, is reduced. Now we will be looking at why this silver nitrate is better than sodium nitrate for the primary alkyl halide reactions. So the sodium nitrate actually exists in the ionic nature. That means the structure is basically ionic in nature. So the nitro group is actually an ambident nucleophile. That means it can react both at nitrogen and at oxygen also. So that is why we say the alkyl nitrite is when the reaction occurs on oxygen, and it is a nitro product when the reaction occurs at nitrogen center. So that is the reason we have two different type of product formed when we use sodium nitrate as the nitrating agent. So as I have mentioned, the nitrate ion has oxygen centered one. That means the oxygen attacks the alkyl halide to give the alkyl nitrate as the product, and that means here we have oxygen as a nucleophile. And when we use the other part, that is the nitro part, where the nitrogen is acting as a nucleophile, we end up with our required nitro product. So these are all the two possibilities happening due to the ionic nature of this particular NaNO₂. So that is what given here. So when we use NaNO₂, both this one, that is the nitro product, and the alkyl nitrate, both are formed in higher yield. So that is the reason we are getting an unwanted product in this particular reaction. But when we use silver nitrate, actually here in the case of silver nitrate, the AgN bond is actually partially covalent in nature. So NaNO₂, the Na nitrogen bond is ionic in nature, whereas in the case of silver nitrate, AgN bond is covalent in nature. So because of that, we do not actually have a ambident nucleophile involved in this particular reaction, which leads to nitro compound formed as the major product and not the alkyl nitrate. So that is the reason people prefer to use silver nitrate in these kind of reactions. Since this reaction is a SN2, that means nucleophilic bimolecular substitution reaction, primary alkyl halides gives better yield of the product. You would have studied about the Victor-Meyer test. Let us recall what is this test. This is actually used to study about the primary, secondary and tertiary alcohol comparison. So in this method, basically the sample alcohol is treated with Pi3 to get the iodoalkane. So once the iodoalkane is formed, it is then treated with silver nitrate. When we treat the iodoalkane with silver nitrate, we end up with the nitroalkane. So this is actually the crucial species that is involved in the Victor-Meyer test. Once we have this nitroalkane, then the nitroalkane is treated with nitrous acid, that is NaNO₂ and HCl, and the resulting solution whatever we get is treated with the KOH, and we will observe what is the color that is being formed. If it is a primary alcohol, a red precipitate is formed. If it is a secondary alcohol, a blue color is obtained. When there is no color, we say tertiary alcohol is present. So this is how the Victor-Meyer test is being conducted, and the major reaction which is involved in this particular case is the formation of the nitroalkane. And of course, tertiary alkyl halides does not react with the silver nitrate, so that is the reason there is no reaction. So the nitroalkane is not at all formed. So when the nitroalkane is not formed, that means the Victor-Meyer test does not occur, or Victor-Meyer reaction, this particular reaction does not occur. So let us look at the next preparation. This is from the halogen-acetic acid. So this is mainly applicable for nitromethane only. So other nitroalkyl derivatives are not prepared by this particular method. Here what happens is the halogenoacetic acid, that means the chloroacetic acid, the sodium salt of the chloroacetic acid is treated with the NaNO₂. By the formation, this leads to the formation of nitroacetic acid. Once the nitroacetic acid is formed, we have strong electron withdrawing nitro group. So what it does is it actually pulls the electron towards itself, and the carboxylate ion is actually lost as the CO2 molecule here. So that is how this is lost as the CO2, and what we end up is the nitromethane. So that is why in this particular case we have only 35 to 38% of the yield. In other words, this reaction is not a very efficient reaction. Even for primary alkyl nitrate, that means for the nitroalkane, we only get close to 35% yield. So this reaction generally does not give a good yield for higher analogs. So that's the reason this method is not used to prepare higher analogs. Let us look at the next one, which is the industrial process. So in the industrial process, we have two major methods. First, let us look at the liquid phase nitration reaction. So in the liquid phase nitration, we are actually using concentrated nitric acid at 140 degrees centigrade under pressure. This reaction is a very slow reaction, and this also leads to polynitro compounds as the side products. Sulfuric acid nitric acid combination does not nitrate aliphatic compound, because this combination, sulfuric acid nitrate combination, is the most preferred one for the aromatic electrophilic substitution reaction, whereas in the case of aliphatic system, this combination does not give nitro compounds. And when we are using this industrial process in the liquid phase nitration, only the hydrogens are replaced by the NO₂ groups. That means alkyl substituents are not replaced. So this is one thing we will be looking at when we are looking at the gauge phase reaction. We will also see like what are the other reactions which are happening. So we have a methyl group here. This methyl group is actually not replaced, and we have a hydrogen which is attached to one of the terminal carbon. So this methyl group hydrogen is replaced by the nitro group. So that is how we end up with our final product. And as there is also another hydrogen in this particular secondary carbon. So this 2 carbon is here we have a methyl group. So this carbon has one hydrogen atom, and this hydrogen atom is also replaced by the nitro group. So that means the hydrogen atoms are actually replaced by the nitro group. And nitric acid being an oxidizing agent, what it does is it even oxidizes obtained nitro compounds to carboxylic acid also. So that is the reason here this method cannot be used for the preparation of nitro compounds effectively, because instead of the required nitro derivative, because this is the nitro derivative we wanted to prepare, but instead of this single nitro derivative, we are getting another additional polynitro derivative, and some of the molecule is also broken down into the carboxylic acid. So in other words, what we can say is this liquid phase nitration is not an efficient method for the preparation of nitro compounds. So why we get the polynitration? That is a question we have to answer. The starting material alkane is not easily soluble in the nitrating mixture, whereas when it it undergoes the first nitration, this nitro derivative is more soluble in the nitrating mixture, that is the nitric acid, and which increases the substitution of hydrogen with another nitro group. So that leads to polynitration. So that is the reason the increased solubility of the formed product leads to polynitration. And there is a second method in industrial process. So this is basically the gas phase nitration reaction. So in this particular case, so this reaction is actually governed by Haass-Schichter rule. So here we have a couple of things happening. We will be looking at what are each individual ways by which the reaction actually proceeds. So here the reaction is carried out using concentrated nitric acid, and the temperature is very high, 150 to 475. In the case of liquid phase nitration, we only have up to 140 degree and under pressure, but in the case of gas phase nitration, we are going to very high temperatures. Here higher alkanes generally produce polynitro compounds. So the lower alkanes actually give the required product, but when we use higher alkanes, that leads to polynitro compounds. At low temperature, what happens is the replacement of hydrogen is following this order. Tertiary hydrogens are replaced very fast compared to secondary hydrogens, followed by primary hydrogens. So when we take the example, we can actually look at how the reaction actually proceeds. So what is going to be the major thing? So here we have a hydrogen here, we have a hydrogen attached to this terminal two carbons. So when we have hydrogen attached to the terminal two carbons, they undergo nitration to give the corresponding nitro derivative, and here we also replace one of this hydrogen atom which is present in the secondary position. So here also the substitution takes place, and this molecule also breaks down into further products like the nitromethane is formed as one of the product, and nitroethane is formed as one of the product. Here nitromethane is formed as a product, and we also have substituted compounds. Nitropropane is formed as one of the products. So in this particular case also we have various reactions which are happening. As we have mentioned, since the temperature is high, the reaction also leads to alkyl side chain replacement. So here the CC fission reaction actually takes place at higher temperature, but in the case of liquid phase nitration, this reaction does not happen. And the nitric acid is actually acting as both a nitrating agent as well as oxidizing agent. So when it acts as an oxidizing agent, we end up with various side products like alcohols, aldehydes, carboxylic acids, etc. are formed. And when we use catalysts like copper and iron to facilitate this reaction, actually oxidation occurs more than the nitration. So these are some of the limitations of gas phase nitration. All these are called Haass-Schichter rule because they have studied this nitration elaborately, and they have identified what are all and how the reaction actually proceeds. Say for example, how the replacement of hydrogen takes place, and where the alkyl the CC fission bond happens, and what is the role of the nitric acid as a nitrating agent as well as the oxidizing agent, and what are the side products like carboxylic acid, alcohols, aldehydes, etc. are formed, and what is the role of the metal catalysts, especially iron, copper, etc. had been studied elaborately by Haass and Schichter. So now the next question is, why do we call this industrial process an important one for the preparation of nitro compounds? Because when we are using the nitro compound, in the overview we have seen that nitro compounds are generally used as solvents. So when we are using nitro compounds as a solvent, we are actually not worried about whether it is a single individual compound or it is a mixture of compounds. Say for example, when we talk about gasoline or petroleum product, we actually have various alkyl groups are present. For example, we simply say C5 to C8 fraction, C3 to C6 fraction. Like that, we actually call that like a normal, and the branched groups are also present in the normal petroleum products. So all branched compound can be used in combination. So that is the reason in the case of nitro compound also, even though we end up with a mixture of nitro compounds, they can be used as a solvent, that is a reaction medium for a particular reaction. So that is the reason the industrial process is mainly used for preparing these kind of very important solvents. When we need a very pure alkane, say for example in the previous reaction we have seen both nitromethane and nitroethane are formed, and even nitropropane is formed. So we have C1, C2 and C3 nitro derivatives are formed. If we want very specifically nitroethane, then we can actually do fractional distillation to identify this particular product. So the major advantage of industrial process is to make a large quantity of the product, and depending on our final usage we can actually go for the mixture of nitro compounds as a solvent, or we can also fractionally distill to get the individual nitro compounds. If we look at the proposed mechanism for this nitration reaction, that is a industrial process, the reaction actually proceeds via the AgNO form. So the AgNO form is given here. So in this particular case, the nitric acid is actually written as OH and NO2. So this actually adds, the hydroxy group actually adds to this with the AgNO form is added to the carbon, and we end up with the AgNO form. So once we get the AgNO form, this actually undergoes tautomerization to give the nitro compound, because this AgNO formation can be used to explain the other oxidized products. We are getting aldehydes, ketones and other things. So to explain the formation of the acids, aldehydes and ketone, this AgNO form is actually shown to be one of the intermediate involved in this particular reaction. So when we are going to explain any reaction mechanism, we do need to have some intermediates which can be used to explain how the reaction actually proceeds. If we directly say NO2 is the one which directly adds to this system, then we cannot explain the product formations like aldehydes and ketones and etc., which are formed as a byproduct in this reaction, because there is no way a nitro group can be converted to an oxygen or hydroxy group. So these are not possible. But when we look at the AgNO form, so this alkene bond can be broken down, and then we can actually add, because the reaction is carried out in the presence of nitric acid, which is an oxidizing agent. This can actually cleave this alkene bond, and this can actually lead to our observed products like aldehydes, alcohols and carboxylic acid. So that's the reason we say this reaction actually involves AgNO form or other nitro isomers, like we have also seen both the primary and secondary, that alkyl groups which can be replaced, that is the CC fission happens in the gas phase nitration. So that CC bond formation or the CC bond fission reaction is also one of the important step involved in the nitration reaction. So there is also another method. This intermediate can undergo reaction by the NEF reaction. So this is one of the so the formed nitro product may undergo NEF reaction into ketones and nitrous oxide. And once the aldehyde is formed, the aldehyde can further undergo oxidation in the presence of a strong oxidizing agent, nitric acid, to give the corresponding carboxylic acid. So these are all the various mechanism by which the reaction actually proceeds. The next one is the oxidation of amine. So tertiary amine can be oxidized using KMNO4 to the corresponding nitro compound. That's what this amino group can be converted into the nitro group in the presence of KMNO4, which is a strong oxidizing agent. Hydrolysis of alpha nitroalkene can also lead to the final product. So we have the alkene unit, we have the nitro compound here. So this alkene nitrile, that is the alpha nitro olefins can be hydrolyzed using water to give the carbonyl compound and the nitro compound as another product. So here also what happens is basically this double bond, that alkene bond cleaves, and we add oxygen here, and this part is actually formed as a, here we have to add 2 hydrogens, so H2 and another hydrogen is here, so we have the CH3 unit, so CH3NO₂ is formed here as shown. Next we will move on to the reactions of nitroalkanes. So nitroalkane has various functionalities. We have a electron withdrawing nitro group, so this will facilitate reactions. What are the type of reaction it will facilitate is basically when there is a electron withdrawing group, this particular hydrogen becomes highly acidic. So when we have a acidic hydrogen, so the acidic hydrogen can be easily removed by a base. So the base abstraction of this acidic hydrogen leads to a negative charge on this particular carbon. So this is one of the way we can generate a nitronate carbon. This anion is called nitronate anion, and this nitronate anion is a very good nucleophile, so this can undergo various reaction, and this site can also be used for the arylation reaction. So in other words, the presence of nitro group actually activates this particular carbon to undergo various reactions. And this nitro group also can be reduced, or this can also undergo various reactions. Say for example, reduction reduces this nitro group to an amino group. We can also carry out a hydrolysis reaction, halogenations, and Henry reactions, Mannich reaction, and Neff reactions are some of the named reactions which we will be looking at now. So the first one is the reductions of nitroalkanes. So there are different types of reductions possible. The first one is the metal catalyzed reduction in the presence of acids, that gives a amine. So nitro compound in the presence of an acid. So this is very important. Iron HCl or nickel can be used to prepare amines. So this is the first reaction. This reaction actually happens in the presence of acids. But if we do the same reaction under neutral conditions instead of an acid, we end up with basically the hydroxylamine derivative. So this is the hydroxylamine derivative. This is the R group which is attached to the hydroxylamine. Hydroxylamine is NH2OH is the hydroxylamine. So one of the hydrogen is replaced by an alkyl group. So this is the hydroxylamine derivative, and this reaction is carried out under neutral conditions. So here instead of HCl we are using ammonium chloride, and again this is a metal catalyzed reaction. Zinc is used in this particular reaction. So in the presence of zinc and ammonium chloride, in the presence of hydrogen also, the nitro compound is converted to hydroxylamine derivatives. When we use stannous chloride for the reaction in the presence of HCl, we get actually hydroxylamine derivatives and oximes also. So this is the hydroxylamine derivative which we have seen earlier. So in the presence of SnCl4 and HCl, we are going to get another additional product which is the oxime. So if you look at how the reaction actually proceeds, the nitro compound loses oxygen to give the nitroso compound, which on reduction gives the hydroxylamine derivative. The other isomeric form of the nitro compound, which is acinitro, on reduction gives oxime. That is what this reaction actually gives the final product. Next is hydrolysis reactions of nitroalkanes. Primary nitroalkanes on hydrolysis, especially in the presence of sulfuric acid and heating, gives hydroxylamine and other corresponding carboxylic acid. In the case of secondary nitroalkanes, this reaction actually gives stars, and the tertiary nitroalkane do not react. So this is mainly for the primary nitroalkanes this reaction is applicable. So we end up with a carboxylic acid derivative. So the hydrolysis of the nitro derivative gives a carboxylic acid. So here you have to look at the number of carbon atoms. The starting material has 3 carbons, 1, 2 and 3, and the final product also has 1, 2 and 3 carbon atom. So here we are not losing anything, we are only losing the nitro group is lost, no carbon is lost for this particular reaction. The nitro group is lost as the hydroxylamine. So in the case of secondary amine, we don't get this reaction very efficiently, as it is mentioned for the tertiary nitroalkane, they do not even undergo this particular reaction. We have seen that nitro compounds can exist as a acynitro form, because tautomeric form, acynitro and nitro forms are the two tautomeric forms. So at any given point of time, there is a tautomerization occurring in this particular compound. So the nitro compound, when we actually do this same reaction, this can also undergo in the acynitro form. So when it undergoes the reaction under acynitro form, we end up with a carbonyl compound. So aldehydes are formed, and as we have mentioned, there is a hydrogen atom on this alpha carbon. So when we have a hydrogen atom on at least one hydrogen atom in the alpha carbon, then the nitro and the acynitro tautomerization actually occurs. And most of the time it is the preferred isomer is the nitro form is the most stable one, but acynitro form is also formed in very small quantity. So one of the hydrogen shifts from the carbon atom to the oxygen atom. So this is what happens, that in tautomerization, a shift of hydrogen atom takes place. So the alpha carbon loses one hydrogen and the oxygen takes up that particular hydrogen atom. So let us move on to the next reaction, which is a halogenation reaction. So nitroalkanes undergo halogenations. That happens because of the electron withdrawing nature of the nitro groups. As we have mentioned, this particular alpha hydrogens in the primary and the secondary nitroalkanes are acidic in nature. So that's what we have seen earlier. So this acidic hydrogen is being replaced. They are generally replaced by the halogen atom, and this reaction actually happens under alkaline conditions if this reaction proceeds efficiently. So in the presence of a base, this is a acidic hydrogen, and this acidic hydrogen can be abstracted by a base. So we end up with an anion formation here. So this anion now attacks the halogen atom, and this is lost, which leads to the substitution of one of the hydrogen by the halogen atom. So this is what is the substitution reaction of alpha hydrogen in the nitro compounds by the halogen. For example, chloropycrin is one of the compound. This compound is prepared from this halogenation reaction from nitromethane, chlorine and sodium hydroxide. Sodium hydroxide is the base that is used, and chlorine is the halogen atom, and this chlorine nitromethane has 3 hydrogen atoms. So all the 3 hydrogen atoms are replaced by chlorine atom. So that is how the chloropycrin is formed. Next one is the reaction with the nitrous acid HNO₂. So the addition of sodium nitrate to an alkaline solution of the primary or secondary nitroalkane followed by acidification gives nitrolic acid and pseudo-nitrol respectively. So we have seen that how the reaction actually happens, but here we will look at what are the products that are actually formed. So this is the primary nitroalkane. So how do we get the primary nitroalkane? The alcohol is treated with the Pi3, so we end up with the halogen compound, and this halogen compound, the haloalkane, is treated with AgNO₂, and this AgNO₂ leads to the formation of the nitro compound. So this is our starting material for the Victor-Meyer test. So in this particular case, the nitro compound reacts with nitrous acid. So last step is the reaction of sodium nitrite with the HCl. NaNO₂ and HCl both together react to produce HNO₂. So this is what is the reaction which is happening, and once the HNO₂ is formed, this HNO₂ will react with the reacts with the nitro compound, and that leads to the alkyl nitrolic acid in the case of primary nitroalkanes, and when this is treated with a base, we end up with the red color. And if it is a secondary nitroalkane, the same reaction gives pseudo-nitrol, and this pseudo-nitrol gives a dark blue color. So this is how the primary and the secondary alcohols are differentiated by the Victor-Meyer test. The next one is the Henry reaction. So here, as we have seen earlier also, this particular alpha hydrogen on the nitro derivative can be abstracted by the base because this is the acidic proton. So this acidic proton can be abstracted by the base, and this leads to the formation of a carbanion. So once the carbanion is formed, this carbanion can react with the carbonyl compound. So this is what the reaction, if it is when there is no nitro group present in the compound, we call this as a aldol reaction. So that is what it is given here. So if it is an two molecules of the aldehyde which have the alpha hydrogen atom in the presence of the base, they condense with each other to give aldol product, and instead of the two aldehyde compounds, if one of the compound is having the nitro group if nitro group is present, then that reaction is called the nitroaldol reaction. So we are using a nitro derivative and then aldehyde or carbonyl derivative. So this reaction is called the nitroaldol reaction, and this is also the name reaction for this one is the Henry reaction because this was discovered by Henry. So the primary or secondary nitroalkanes in the presence of base catalyst react with aldehydes or ketones to give the beta nitro alcohol. So this is what is called the nitroaldol reaction, and the beta nitro alcohol can be either dehydrated to give the nitroalkanes, or the hydroxy group can be oxidized to give the alpha nitroketones, or they can be reduced to give the corresponding amino alcohols. So when we have the hydroxy unit, we have the nitro unit. So what are the different reaction can happen? One, the nitro group can be reduced to the amino group. So this is possible. When we just reduce the nitro group, we end up with the amino alcohol. Okay, so this is one product. And now the hydroxy group is, if it is present in the secondary carbon, then we can actually oxidize this to the ketone. So we end up with the nitro compound remains as intact, the nitro group remains as intact, and the hydroxyl is converted to carbonyl group. If it is a hydroxy unit, that is a secondary alcohol, we oxidize that to the carbonyl compound, that is the alpha nitroketone is formed. The next one is a Mannich reaction. So in this particular case, a primary or secondary nitro compound, they have to have at least one active hydrogen. So what are the reactions we are actually looking at? All have the alpha hydrogen. At least one of the carbon, that is the alpha carbon, should have one hydrogen atom. So then only a base can abstract this particular hydrogen atom to give the anion. So this particular hydrogen is replaced by the, it is abstracted by the base to give the corresponding anion, and this anion now reacts with an aldehyde in the presence of ammonium chloride. So in the previous Henry reaction, we are only treating these two things together. There is no ammonium chloride which is involved. So this ammonium chloride is basically the nitrogen source or the second ammonia derivatives. So this leads to the corresponding aminomethyl derivative. So in this reaction, this is formed as a hydrochloride salt and water is also eliminated. So in the Henry reaction, we do not use ammonium chloride, but in the case of Mannich reaction, we actually use ammonium derivative. So depending on what is the ammonium derivative we are using, we end up with the corresponding nitromethyl derivatives. The next one is the NEF reaction. So what is this NEF reaction? So the nitro compounds on, this is basically the hydrolysis of the nitro compounds. So hydrolysis of this nitro compound leads to the formation of carbonyl derivatives. So this is the overall reactions. How the reaction actually proceeds is basically the nitroalkane is first converted to their sodium salt, and then these are hydrolyzed by sulfuric acid. So this is basically a two-step reaction. So in the first step, we use a base to form the corresponding salt. So the sodium salt is formed in the first step, and then this salt is treated with sulfuric acid to give the final product, that is the carbonyl compound is formed. So this reaction is named after the scientist Neff, who first discovered this particular reaction. And nitrous oxide is formed as a byproduct. This is a gas. So because of this reaction, because of the formation of the N2O gas, this reaction proceeds efficiently. And of course, nitro compounds have both good and bad effects. In the drug development, we have seen about the Henry reaction. So the Henry reaction is used in various drug development. For example, some examples are given here. Bastatin or cytoxazone or acosamine are various compounds which are prepared using Henry reactions. So here we have the amino group and the hydroxy unit. So these are formed by the reduction. The nitroaldol reaction actually gives the corresponding nitro alcohol derivative, and this particular nitro group is reduced to the amine to get the final product as shown here. And there are also other cases like toxic material or toxic compounds are involved. Say for example, nitro group is also involved in the toxic reactions. So there is one mesotoxin is present in various plants, and this compound on catabolism produces 3-nitropropanoic acid. So this 3-nitropropanoic acid or 3-nitropropanol is formed when this particular mesotoxin was hydrolyzed or catabolized. And these compounds, especially the nitropropanol and the nitropropanoic acid, are highly toxic and they are poison to livestock. So the nitro compounds, some of the nitro compounds are actually harmful to the animals and plants. And there are also various explosives which are formed. For example, many nitro compounds are explosives. Why nitro compounds are explosive, we have to understand, because if you look at many of the organic compounds, we have carboxylic acid, we have aldehydes, we have ketones, we have halogenate derivatives. None of them is generally used as an explosive, but only the nitro compounds. So why the nitro compounds are used as an explosive? Because the nitration reaction itself is an exothermic reaction. That means the delta H for this particular reaction itself is minus, delta H is negative. In other words, when we are doing the nitration itself, many times that leads to explosion. So that is one of the reason. And when we have to call a reaction to be an explosive, just having the exothermicity of the reaction alone is not sufficient to call some reaction as a explosive reaction. The reaction also should produce large amount of heat and pressure. That means a gaseous product should be formed in this reaction. Whenever large amount of gaseous products are formed in a particular reaction, and also if the reaction is exothermic in nature, we call those kind of reaction as explosive reaction. And this has to happen instantaneously, not over a period of time. Say for example, when we have the NO2 group, that is the nitro group, the conversion of the nitrogen, in this particular group, the nitrogen is in the high energy level. That means this is in the high energy level. And in the case of nitrogen gas, that is the same nitrogen is in the low energy level. So that means we have the nitro group. This nitrogen is in the high energy level. This is getting converted to nitrogen gas, which is in the low energy level. So that means we are moving from a high energy state to the low energy state. When we are moving from high energy to low energy state, lots of energy is actually being released. So that is one of the reasons these reactions are highly exothermic and they release high energy. And the second, in the nitro group, we also have O2. That means oxygen is also present. What can oxygen do? Oxygen is a very good oxidizing agent, and this actually burns the alkyl chain in the nitration reaction. When we are running various nitration reactions of alkyl substrates, this oxygen actually burns the alkyl chain. So that means lots of energy is also produced by this particular reaction also. So overall, when we have to say, the explosion process generally generates basically heat forming highly stable products like nitrogen, carbon dioxide. So these are gaseous products which are quite stable products which are produced in that reaction. So that means large amount of energy is released in this particular process. And for example, if we take ammonium nitrate and when we heat it, we actually get N2O and water. We don't call this reaction as an explosive reaction, but when the same reaction produces nitrogen gas, oxygen gas and water molecule, we call this as an explosive reaction because this is an instantaneous reaction and this reaction proceeds with enormous amount of energy. So same compound, that ammonium nitrate, can actually undergo simple decomposition or it can also explode. So these are all the two different ways by which the reaction actually proceeds. Instantaneous reactions are called explosive reactions and normal reactions are called as decomposition reactions. So there are some examples of nitro derivatives as explosive. We have seen that a nitro compound which is having the molecular formula CNO₂ is in which case the carbon and the nitrogen are connected directly. That means the nitro group is attached directly to the carbon. These are called as nitro compounds, and some examples of nitro compounds are DNT, trinitrotoluene, etc. 2,4-dinitrotoluene, 2,4,6-trinitrotoluene. These are some examples. If you want to look at the nitrotoluene structure is given here. Toluene has a methyl group on benzene ring. So we have a nitro group here. So there is a carbon nitrogen bond. We also have another nitro group. So this is a 2,4-dinitrotoluene. So here again we have a carbon nitrogen bond. So when we have a carbon nitrogen bond, those compounds are called as nitro compounds. And we also have nitrate esters. So this compound we have seen earlier also. So in this particular case, the nitro group is actually attached to the oxygen atom. So these are called nitrate esters. We have seen alkyl nitrites earlier. So what is alkyl nitrate? We have RO-NO bond which is formed. So in this particular case, oxygen, nitrogen, there is a bond. So they are called alkyl nitrate because oxygen alkyl group is attached to the oxygen. But in the case of nitrate esters, what we have is we actually have a O and NO2 bond which is present. So these kind of compound, here we can have an alkyl group. So when we have O-NO2 type group is present, these are called as nitrate esters. And glycerol trinitrate and cellulose nitrate, which are used as an explosive, or nitrocellulose, are some examples of these kind of compounds. And we also have nitramine. So in this particular case, we have a nitrogen N nitrogen bond is formed. So NO2 and N are connected together or bonded together. So these kind of compounds like for example RDX is one of the very powerful explosive which has a nitrogen and nitrogen bond. That means this is having an example of nitramine derivative. So these are all the various examples of nitrogen as nitro compounds as explosives. With that we conclude this particular session. Let us recap in the summary. Let us recap in the summary what we have studied so far. We have studied about the structure of nitro compounds. We have actually studied what is the resonance structure of nitro compounds, and they are actually having high dielectric constants. They are actually polar compounds. So the nitrogen has a full positive charge and both the oxygens are having half negative charges, which is very similar to or isoelectronic with the carboxylate anion. So all those things we have studied, and we also studied what is the most stable resonance structures for nitro compounds. Then we studied about various preparations of nitro compounds, how alkyl halides or amines can be converted to nitro compound we have studied. We have also studied about the industrial process, that is the liquid phase methods and the vapor phase methods, and we also studied about what is the criteria or the rules governing the nitration of nitration. Later on we studied about the various reactions of nitro compounds. We first studied about nitro compound getting converted to amine using reduction reactions. We also studied about the hydrolysis and the halogenation reactions of nitro compounds. Later we studied about the Henry reaction or the nitroalkyl reaction, where the nitro compound should have at least one alpha hydrogen From that we actually generate a base, and that base reacts with the carbonyl compound to produce a product which is similar to the aldol. So, that is why this reaction is called the nitro-aldol reaction that we have studied. We also studied about the Mannich reaction. If the same reaction is carried out in the presence of ammonium chloride or amine derivatives, what are the products that are formed, that also we have studied. Then finally we studied about the NEF reaction, that means conversion of the nitro compound to a carbonyl compound, especially ketones we have studied. With that we conclude this session on nitro compounds. Thank you.